Good evening, everyone. Welcome to the 4-day online workshop on analysis techniques for material characterization under SSR scheme of DST SAIL project. As we all know, this is the third day of online workshop. Myself, Richu Rajan, Research Scholar, Department of Physics, MA College, Kodamangalam. All participants are requested to turn off the mic and video. Let us start our session with a silent prayer. Thank you all. It's my pleasure to welcome you all to this wonderful event. As already mentioned, today's section is heading by Dr. Jemy James, Support Engineer, Witec Oxford Instruments. On the topic, Raman Spectroscopy. I cordially invite Dr. Sanu Matthew Simon, Assistant Professor, Department of Physics, to introduce the speaker. Thank you.
Richi, am I audible?
Yes, sir.
Yes, you are.
Good, thank you. Dear participants, I hope you have been enjoying the insightful sections in our 4-day online workshop on analysis techniques for material characterization so far. Today, as we start on the third day of this workshop, I am excited to introduce our distinguished speaker, Dr. Jemy James. Dr. Jemy is a renowned expert in the field of material characterization, and we are truly privileged to have him as our speaker today. Dr. Jemy serves as a support engineer at Witec GmbH, a leading supplier of instruments. He completed his PhD from University of South Brittany in the topic Refractive Index Engineering. Dr. Jemy finished integrated MSc Photonics from Cochin University. His work has been recognized internationally and published numerous research papers and articles on refractive index engineering. In today's section, Dr. Jemy James will handle Raman spectroscopy. His insights and expertise will undoubtedly enhance our knowledge and understanding of this crucial aspect of material characterization. Before we welcome Dr. Jemy to the virtual stage, I would like to remind you all to stay engaged and feel free to post any questions you may have in the chat or question and answer section. We will have a dedicated time for questions at the end of his presentation. So without further delay, let's extend a warm welcome to Dr. Jemy James, our speaker for today's section. Dr. Jemy, we are eagerly looking forward to your presentation. Thank you.
Thank you, Dr. Sano, for your kind words. Am I audible?
Yes.
Yes, sir.
And is my screen visible?
Yeah.
Okay, fine. So, thank you, Dr. Sano and the whole organizers for inviting me for this session. So, this session will be on Raman spectroscopy with correlative microscopy techniques. I understand that you're having a diverse audience with very different background. So I'll try to make it as simple as possible so that even the undergraduate students or the postgraduate students can understand, and the researchers can also understand the technique in detail. To start with, this presentation will be a mix of a presentation, and then I'll be showing you a live demonstration of the data analysis of Raman data. So let me just go into my presentation. So before I begin, so I work for Oxford Instruments. Oxford Instruments had acquired Witec in the year 2021. So Oxford is a big company, which is like a spin-off from University of Oxford, and it has different businesses like Andor cameras, Asylum, AFMs, magnetic resonance, nanoanalysis, and things like that. And its applications products include atomic force microscope, deposition tools, low temperature systems, optical imaging, NMR, and a lot of things like that. So VTech is an outcome from a research group in the year 1997. It, it's somebody like you who had three of them had joined together in 1997 from University of Ulm in Germany, and we have a headquarters at the Science Park in the University of Ulm. So we also have different kinds of measurements systems like Raman imaging microscopes, scanning probe microscopes, correlative microscopes, and a couple of softwares related to those things. So in India, we are there in Bangalore, and there are four of us are there. And we have around 80 systems across India, and we have a demo system in India in which we are always welcome to have online booking for the demo system for some sample analysis. So as you all know, so C.V. Raman developed this Raman effect on the eve of February 27, 1928. So initially they didn't have, people used to use sunlight for the measurements. And the sunlight was passed through a mirror, and then a violet band pass or violet filter was kept into the scattering of into a liquid. And then this, you had kept, let me just highlight using a pen. They had kept a green band pass filter so that you can see the Raman spectrum. This was just a summary of the measurement which it was carried out during that time. So this was a Raman spectrometer, then used in 1928. The story is that Sir C.V. Raman and Dr. K.S. Krishnan, this is basically the Raman spectrograph, in which the Raman spectrum was obtained in 1928. I happened to go to the Indian Academy of Cultivation of Science in Calcutta last month, and this is a photograph of the spectrograph. They have maintained it well. And the story is that Dr. K.S. Krishnan and Dr. C.V. Raman was working on this. And on February 27th evening, they discovered this, but they couldn't confirm it. So because the sun had set that day. So again, they started on the next day, waited for the sunrise. So the next day, and on February 28th, they were able to confirm the Raman effect. That's why we have the National Science Day on February 28th on every year. So the Raman technique is basically you have an incoming radiation which interacts with the chemical bonds of a sample, and due to the vibrations and the interactions, the emitted light will be of a different wavelength. So this Raman spectroscopy can give you immense information about the chemical nature of the material, and it is a non-invasive technique. And it is really beneficial for all stratas of life. Some of you might be aware of optics and the interaction of light with material. So when you have an incoming laser, it interacts with the material. There can be three possibilities. One is that the same output of the wavelength will be emitted. It is called Rayleigh scattering. You can see the energy of the incoming and outgoing radiations are the same. Then you have something called as Stokes-Raman scattering, in which the scattered light will have a higher wavelength. As you might have studied in your basics, higher wavelength means lower energy. That's what you can see here. There's a lower energy here. There is something called as anti-Stokes-Raman scattering, in which the emitted radiation will be having lower wavelength, that is higher energy. That is called anti-Stokes-Raman scattering. So before you jump into any kind of microscopy, you have to understand the limits of the microscopy. So the normal optical microscopes has a resolution limit of around 1 micron, in which you have the bright field microscope or dark field microscope, fluorescence microscope, and polarized microscopes. In the case of confocal microscopy, like Raman spectroscopy and fluorescence, you are limited by the resolution of 320 nanometers. You can't go beyond that. Then you can depend on scanning electron microscopes, in which you can go in the range of 1 nanometer and to 5 nanometer and above, like SEM, TEM, and things like that. And if you want to go to sub nanometer regime, you can use a scanning probe microscopes like AFM and things like that. In the case of correlative microscopy, you can have an optical microscope coupled with an SEM, or an optical microscope coupled with a confocal, or you can couple a confocal with Raman, or photoluminescence, or lifetime, and many of the things possibilities are there. So this is for a beginner point of view. In the case of an optical microscope, a light falls on the sample, and then it can fall on the observer. Then this observer can adjust the focus and things like that, get a better image. After that, this can be captured into a camera like this. And then you can have polarized light microscopy, in which you can use the polarization of the light source to image particles, which is in a homogeneous or heterogeneous mixture, and thereby you can identify them using the polarized light microscopy. In the case of confocal microscopy, you might have seen the previous picture, the light source. The light is coming down, and you can see that the light will be focusing in different locations. So the whole rather than falling into a single point, the light will be falling into a larger cone, and the whole light will be coming to the camera. So you'll not be able to get a resolution, because there is out of focus light and in focus light. So you introduce something like a pinhole in front of the camera, so that you prevent the out of focus light from falling into the camera, and you allow only the in focus light to fall into the camera. This is the basics of confocal microscopy. When you have a confocal microscopy combined to a spectrometer, you get a confocal Raman microscope. So this is a spectrometer in which you have the light, the confocal Raman signals coming into the lens. It falls onto optical element called as grating, and then it falls onto the lens into a camera. So you can combine a confocal microscope and Raman spectroscopy. That's what we call it as confocal Raman spectroscopy. It's basically very much useful in the case of understanding materials as such. So you can see a confocal microscopy image, which is basically a confocal Raman image of an embryo cell. So you can see the information related to, I think you'll not understand anything now. As our presentation progresses, you'll be able to understand much better. So what are the basic parts of a microscope? So you have a laser, in which first you have an optical microscope. The light falls onto the sample. You are using an objective and gets back to a camera. You can understand the sample. Then once you identify the sample by your optical microscope, you have the laser, from which the laser is coupled to the sample, and then it get back to the microscope output. It falls onto the spectrometer, and then falls on the grating, and then falls on the CCD camera. So these are the basics of a confocal Raman microscope. So what are the components inside it? There is a excitation laser source has to be there. There has to be a microscope has to be there. There has to be an objective lens. Then a microscope has to be coupled with a spectrometer. And the spectrometer also has to be active. Then there is something called as grating, in which which will determine the resolution of the images or spectrum, and then you've got CCD camera. So what does a Raman spectrum tell you? So the first thing which Raman spectrum, I'm jumping directly into the data as because I understand that you need more information related to these aspects. So what does the Raman spectrum tells you? The Raman spectrum, the band position intensity of the Raman spectrum can give you the characteristics of a peak or a polarizability of a bond and things like that, which gives an information about the fingerprint of the molecule. Okay, like everybody has a unique fingerprint, a Raman spectrum will be giving you an information about the molecule as such. And you can understand from the changes in the band intensity, you can understand the chemical structures. Then what does the shift in the band position tells you? So you can see that this peak is at 340 nanometer, the relative wave numbers. Suppose you have another spectrum after some time, after some measurements is carried out, it is at 350 relative wave numbers. What this is called as peak shift. This peak shift will give you an information about the change in chemical structure or pressure or stress or temperature. Recently, I was approached by one of the companies in which they make materials like silicons and things like that. It's something called as PDMS. They want to understand the changes in one particular bond of this PDMS before aging and after aging. You all might be traveling in any kind of vehicles, right? So these vehicles or the windshield of the vehicle will be having a silicon gel which will be wrapping the glass or the windshield to the material of the vehicle, right? So we should be researchers who make these materials. We'll have to understand the changes in this material when it is exposed to sunlight, when it is exposed to rain, and when it is exposed to heat, all those things, right? And when it's so all these things you need to understand. So you can take the help of a Raman spectrometer or a Raman spectrum to understand what happens to the chemical structure or what happens to the material when it is under pressure, when it is under temperature and things like that. And then when you have a polarizer also into it, the Raman spectra can give you information about the orientations also of the crystals. So again, if the peak width is changing, suppose if you had a peak like this initially, and then finally after some measurements or after some kind of external application, you have a peak which is of pretty narrow, like this, it can give you an information about the quality of crystallinity or doping, amorphosity and things like that. I'm not saying that this will give you information exactly like an XRD, but it can throw light into the quality of the crystalline nature of the material. More narrow the spectrum means more is crystallinity or crystalline is it will be more crystalline in nature. Now, looking into some of the spectra. So you have a carbon nanotube on a silicon substrate. Then you can get the spectrum of the silicon. This is the first order of the silicon spectra. This is the second order of the silicon spectra. And you will get the carbon nanotube's particular band. So if any of you are new, carbon can give bands in multiple regions, and we call them as G band, graphitic band, defect band, and then 2D band and things like that. So this is a band, this is a spectrum of a carbon nanotube on a silicon substrate. So once you do a Raman spectrum and Raman imaging, you get a understanding of the thickness or the diameter of the carbon nanotube. So sometimes you need to understand the depth resolution also. For example, if you have a graphene, single layer graphene, or a single layer MOS2, or single layer WSE2, and things like that, you need to identify whether a machine can really study or identify the single layers and things like that. For that, you can do a measurement from top to bottom like this, and thereby you'll be able to understand about the depth resolution of the material machine as such. For that, we are using ultra thin graphite or graphene. So what could be the factors influencing the throughput? Throughput means ability of the signal to be, or the information from the sample to be converted to a spectrum. So there are multiple factors like the objectives, the coupling elements, focusing elements, the grating spectrograph, and the CCD. So there are multiple elements which is influencing the throughput. So I'm skipping some of the slides so that I can show you a demonstration using the software itself. Yeah. So when you have a correlative microscopy technique in which you have an AFM and a Raman imaging tube which can be carried out together, one of the some similar machine is there available at Mahatma Gandhi University, Kottayam, in the instrumentation center. So you have the atomic force microscope and the Raman spectroscope combined together. So you can do a Raman imaging of a material, and the same material or the same microscope, you don't want to do anything else, just change one of the turrets and you can do the AFM of the material. Thereby, you can understand the layer thickness or the layer differences or morphology of the material using an AFM image, and you can get an information about the chemical information from the Raman image. And you can correlate these two together. See, you can see from this, you can see about the layers, single layers is available using the AFM, and then you can get it using the Raman image also. So that is advantage when you have multiple measurement techniques when it is combined together. So this is a polarization study when you have a polarization Raman microscope in which you can see in this image, the image to the right, when you have one particular polarization, you see some of the carbon nanotubes, and at a different particular polarization, those are not present, whereas you see something else. So at different polarization, you can understand the different orientation of the carbon nanotubes or any kind of material. This is an example of a carbon nanotube. So the orientations of the material can be identified using the polarization of Raman studies. Then you can see when you have a Raman spectra of a diamond, you can understand from this, from the Raman imaging, and then you can understand it from the fluorescence imaging also. You can see the fluorescence coming from here and things like that from here. It's also used in Raman spectroscopy is also used in the case of biology. So here you have a cell with a carbon nanotube. So you can see this is an optical microscopic image or a white light video image taken through the video camera. You have a spectrum of the cell and you have a spectrum of the CNT. You can see that the spectrum of CNT is different and the spectrum of cell is different. And you can see that once you get an image, Raman image, you can see this is the Raman image associated with the cell, and this is the Raman image associated with the CNT. So you can combine these two together and understand how the CNT is localized in the area of the cell. And this is a combined Raman spectrum. So thereby you can understand in the spectrum point of view, and also you can understand the imaging point of view about localization of any kind of material. Here, this is an example of the cell with the carbon nanotubes. This is another example in which you have epithelial cells of a rat in a buffer. So from this Raman spectrum, you can understand about a different materials in the cell, which is different, which has its own different spectrum. So if you are combining these things, you will get to understand the details of it. Like what is this blue color representing, what is this red color representing, what is this green color representing, and things like that. Thereby you will be able to understand the inside of a cell and things like that. This is also used in the case of pharmaceutical samples. So this image which I'm showing it here is associated with the active pharmaceutical ingredients. So you can see the different polarization. Each color represents different polarization. So thereby you can understand how each crystal is oriented in a same API. So as I told you, Raman spectroscopy can be used in multiple areas. Then you can go for a 3D Raman imaging also, in which you can get a lot of other informations. Like, see, this is a garnet. I mean, one of the rock samples in which it has inclusions of water. It has inclusions related to some hydrocarbons and things like that. And then once you get into a three-dimensional point of view, once you measure the sample in a 3D Raman imaging, and then once you combine all those spectra and all those images, you'll be able to present to the people that how your material is staying inside a three-dimensional host. So here you can see the green spectrum relates, the green image relates to the calcite. Then you have the blue, which is there. You can see the blue region, it is the water, which is inclusion. Then the orangish or reddish are related to the garnet of the rocks. You can also use this for the food, in the case of food, to understand the different kinds of materials, like whether it is a fat and different kinds of fat, whether it is a chemical element. So you might be using a jam, or you might be using any kind of material, a detergent or a shampoo or a soap. It all has multiple materials inside it. So you can identify all those materials using Raman spectroscopy. There's an example in which you can use it in the case of pharmaceutical tablets and things like that. So you can see this red and blue images correspond to the active pharmaceutical ingredient, and then your green correspond to the excipient and things like that. So there's a lot of possibilities to understand the chemical information of the materials using a Raman spectroscopy. So I'll now jump into the data analysis part. First, I'll take you through a quick presentation of that, and then we'll go to the live data process, data analysis. So whenever you get the data, you have to do basic stuff like cosmic ray removal, whether there is any kind of cosmic rays or any kind of errors in the images or spectrum. Then you have to do a background subtraction. Then you have to do a repairing of spectrum if required by smoothing. Then you can understand the true component analysis. So in the case of a spectra or a single spectra which you're getting, first you have to do a cosmic ray removal. What is a cosmic ray? Some of the spectrum will be having something called as cosmic rays, in which you have sharp, very sharp peaks. That may be due to some kind of material, some kind of errors, or any kind of electrical noises and all. So you have to remove those. That is the first step which you have to do. Once you're removing this cosmic rays, you will be able to get a spectrum which is well suitable for the next measurements. So you can see the first spectra, the in red, had the cosmic rays, and the second one is the one without the cosmic rays. So the cosmic rays was removed. This is a raw spectra, and this is a cosmic ray removed spectra. Next, you have to smoothen the graph if required. It is not mandatory, but many of the cases in real practical samples or practical measurements, you'll have to smoothen the data. So there are different possibilities for smoothing the data based on the algorithm available. So we can see raw data and a smoothened data. Thereby, you can avoid unnecessary errors in data, and also you can also give the audience a clearer picture of what is your information, which you want to tell. So there are different kinds of algorithm for smoothing the data. Now you might have done a cosmic ray removal, you might have smoothened the spectra. Then there is something called as background in the spectrum. In order to remove the background, you have to use different kinds of algorithm which is available, like constant or minimum or anything like that. It depends on the kind of application you are using or kind of machine you are using. So in our machine, we have got 4 algorithms in which we can use or remove the background of a material or of a spectrum. So you can see the red spectrum corresponds to the raw spectrum, and then the blue spectrum corresponds to the background subtracted spectrum. So that is the amount of background which is removed. So backgrounds can arise from the initial data or from the kind of fluorescence or different kinds of reasons. So we can remove it from the using the software. So this is another kind of algorithm which you can use. This is also another kind of algorithm. I'm just quickly jumping out. Then when you're talking about carbon, or when you're talking about, I think most of you might be researchers in which you're carrying out multiple measurements of a similar kind of material. So in order to compare the materials, you'll have to normalize the spectra. So I think most of you might be normalizing the spectra using origin. So here also you can use this normalization either to area to 1 or absolute peak to 1 or maximum peak to 1 or maximum peak to 100, which can help you to compare between the different variants of your samples. In some of the cases, you might need to repair your spectra also. For example, when you're doing some measurement, you have got something which you don't want to show to your audience. This is not required for a data analysis, which might be from the substrate, which might be from something else. So you want to remove it. You can repair the spectrum also. Then finally, from the Raman spectrum, you want to understand the material, right? So there's something called as true component analysis, in which I'll be showing all this in a live measurement now. You'll get information about representation of the material like this, and then different spectra can give you a different image. So the previous one was in the sphere, and this is the surrounding material. So thereby you can understand much in details. Okay. So now let's go to the live demonstration of the sample analysis. Dr. Sano, may I know how much time I've left? Have I got? Dr. Sano?
Sir, you will get half an hour more, sir. Half an hour or more.
Yeah, thank you. So let me close all the spectra. So you can see this spectra. So you can see sharp peak coming up there. So that is a cosmic ray. So you have to remove that cosmic ray. So in order to remove that cosmic ray, I'm using my software. I ask my cosmic ray removing software, CRR. Then you can see by varying my parameters. See, just by putting this value here, I can get this cosmic ray removed it from my spectrum. So if I extract it and if I just check overlay the spectrum together, you can see this cosmic ray was removed in the cosmic ray remote spectrum. So that is the first step which you have to do. So once you remove this cosmic ray, you have to do something called as if you required. So let me just take this data separately so that it will be much more visible to you, much more clearer to you. So this is a cosmic ray removed data. Okay. So I've got this cosmic ray removed here, but you can see it is not so smooth. It is having its own noises. So what can I do? I can go and use my smoothing algorithm. Again, in the smoothing algorithm, you can see you can play with the parameters basically. I'll just zoom in so that it is much more visible for you. So I'm just playing with the parameters, mean, filter. Let me show you about average. So to make things much more visible for you, let me increase the thickness of the graph. Okay, so you can see the red is a raw spectrum and the blue is the spectrum you will be getting after the smoothing. So let me just play with the parameters like average filter size. Let me start with 0. Let me see if it is possible. No. Let me start with 1. You can see it is slightly getting smoothened. You can see the noise is getting reduced. If I use 2, it is still getting reduced. If I use 3 and 4 and things like that, it is still getting reduced as such. So my graph is getting much more smoother. But there is a trap in this. Your spectrum should not be destroyed, or you should not lose the intensity in the pursuit of smoothing your graph. So all the time whenever you're doing some kind of data analysis or smoothing, make sure that your spectrum is not lost. I put it back. I use a different algorithm and see like this. Here I can see that I killed my 2 of my spectra in the pursuit of getting a smoothened graph. So I just wanted to show you about this possibility of you killing your own graph by extreme smoothing. That should not happen, okay? So let's put an average value here like this. I click extract the next step. I can go to the third step can be background subtraction. So in the case of background subtraction, I have used a parameters called a shape algorithm. I just click shape and I click extract. So let's compare these two graphs, these two spectra. I'll just drag this into this. And then if I put, this is a cascaded spectra, I just remove the cascading and then put single biscale so that it is comparable. So you can see this is the background which the spectra was having. Okay. So this much was the background in this data, which was removed using background subtraction. So the green was smoothen raw spectra, smoothen graph, and then you have the blue, which is the finally background subtracted, cosmic ray removed, and smoothen graph. So that's what you can understand from this. Then you can use this feature for normalization also. Like suppose if you want to normalize this peak with respect to one particular peak, say, let us see, let me close this. I'll just show you. So you can see, let's see this particular peak. This peak at 919. I want to normalize the whole graph with respect to 919. Okay. So for that, what will I do? I take this, I use a normalization algorithm. I want to make that 919 as 1. So I use maximum peak to 1. Then I can choose my location or my area, which has to be there. So you can see that this has become 1. So it is easy for you to compare between samples. Let me see whether worked or not. Yeah. So basically you didn't want to kill the all the spectrum. You can just simply do it once. I'll just do it once again. Normalize maximum peak to 1. So that it can become 1 as such here. So that was about normalization. Now let me show you something about if you have this was about single spectrum. Now let us see something related to Raman image. Many of you, most of you might have done Raman imaging at one or two places. If you get a Raman spectra or an image like this is a Raman image. So I've done the background subtraction and smoothing and all those things. You'll get spectrum like this. This is just a spectrum, but it contains n number of information. So what will I do? I'll use a filter to understand, or I can even use a Raman TV to understand about the image, how the image will looks like. I'll use this filter first. I'll use a sum filter. So let me try to see what is the how my spectrum at the zero wave numbers is distributed. So I put a filter which is 0 here. So it is like this. Okay. I want to see how the spectrum and other material is other peaks is like. So I keep a filter like this here. I want to see what happens to the next area. I keep it like this. Each peak correspond to each material. Okay, that you should understand. And then I keep one more filter which will be associated with So I can see that each image corresponds to one particular peak and how that peak is distributed across the material. So just for fancy stuff, I can show you how it is in a three-dimensional model also. A 3D rendering of the sample. Okay. So this is how it will look like. It's just a 3D rendering. And then once you get these individual images corresponding to individual peaks or materials, you can extract them all. I've got extracted them all. So what you've got is that you've got multiple images corresponding to each particular peak. So if I keep a filter corresponding to this particular peak, it is not having much information because there is no much material. If I keep it here, it is corresponding to this particular material. So you can see that each peak is corresponding to some kind of material. This is a PMMA, PET or a composite, something like that. Then what we can do is that we can combine these individual images into a single image as such. That's called combine option. So thereby you can, let me just close everything so that it will be much more clear for you. So this is the spectrum associated with the first image. This is this is the image which is corresponding to the first one, second one, third one, and fourth one. So in this case, I remove my first one, delete. Then I've got this kind of spectrum together. So each has blue is represented here, the second one is here, and third one is here. Okay, so let me just combine these three. So you can represent each material or each molecule or each in the composite by various colors and various spectra. Thereby you can tell to your audience that this is my data from the Raman image. This is my data from the Raman spectra. This is my combined Raman image. Thereby, you can show to the audience that these informations I can get, and this is the locations it is. This is how it is located. The application of these things comes, for example, I recently visited one of the manufacturers of tires. They make tires, and you know that tires has radial, most of the tires nowadays has radial tires. So this radial means steel has to be included in the rubber. Steel and rubber, if just if you put steel and rubber, steel can easily slip off from the material. So you have to improvise the steel, you have to improvise the rubber by using some chemicals. So where this location, where this steel is getting improvised on the surface, you need to understand where this material is going on the steel surface. In the case of tires, you should understand whether it is still remaining on the steel surface or it is getting to the rubber surface. So many things like that. So it's pretty complicated to understand the applications of Raman spectroscopy unless you are really working into this area. Now I'll just, as I have promised to Dr. Sano, I'll just quickly show you something related to the atomic force microscope also. So in the case of atomic force microscope or microscopy images also, as I am referring to the machine at Mahatma Gandhi University, which is an AFM cum Raman machine. As I've discussed about Raman, the second part is the AFM part, in which you have a raw image which is shown like this. Maybe I'll just open it using one of my different software. So you can see the first one is a sample. The first one is a sample without background subtraction. Once you do a background subtraction, you can understand the difference between the layers. So you can see layer number 1, layer number 2, layer 3, and layer 4. So these things you will not understand once without background subtraction. Similarly, in the case of a blood cell, we can see without background subtraction, you don't get much information, but after background subtraction, you get really good information. Then this is a gold wire. So without background subtraction, you don't see everything clearly. With background subtraction, you can see the gold wire, nanowires very clearly. Then some of the questions which come from users is, what is the statistics? You can see the errors, roughness like SDR, SDQ, or SA, and all those things. I'll just give you a quick glimpse on the image statistics, which will be useful in the case of atomic force microscope images also. So main 4 parameters which comes into play is roughness average, root mean square, surface squeakiness, and surface kurtosis. SA, SQ, SKK, SKU. Some common rough surfaces which you can see in your daily life. This is the surface of this dosha, and this is the surface of this toothbrush. You can see it is like spikes on a material, right? And in the case of a dosha, it's a pretty smooth surface with holes on it. I'll put 2 more images for you to remember. You can see, I think MA College Kodamangalam will be having this jackfruit and all in those, the pineapple and all in those particular locations, and jackfruit also. So you can see, I want here to closer look at the spikes on this. This is a flatter spike, whereas in the case of a jackfruit, you have a sharper spike. First one is flatter, second one is sharper. So four images you should remember in our next slides. One is a very sharp images of a toothbrush, of a dosha, of a pineapple and jackfruit. Okay. Now let's jump into the what is the statistics dialogues. What does a roughness average or an RA or SA gives? It gives you an it gives you about the I'll just quickly run through this and go to the next slide. Yeah. Average roughness gives you the arithmetic mean of the variations in the z direction. This is the z direction variation. So it gives you an arithmetic mean. That is what is called roughness average. Whereas in the case of root mean square deviation or RMS value, you will get the root mean square of the variation on the surface. So the first one is SA, that is a roughness average. Second one is called RMS or SQ or RQ. Next is something called as skewness. This is something which many of the people who are working in the atomic force microscopy is having a lot of doubts. What is a skewness which means? Skewness means it's a kind of valleys or peaks on a material. So we have seen in the case of toothbrush, you are having more peaks. Whereas in the case of a dosha, you had more valleys. So a skewness of positive quantity means you have more peaks, and a skewness of negative value means you have more valleys. Again, what does this kurtosis means? This here you should understand about our jackfruit and pineapple, which has sharper peaks, jackfruit. So kurtosis gives you information about the sharpnesses of the peak. Okay. So that is a basics, or this is the mathematics behind it. So this will give you a lot of information about the material when it is undergoing an atomic force microscopy. Once you do an image, you can understand, you can draw a line and understand the profile of it, cross section of it, and things like that. So you can see the first one, cross section without background subtraction. The second was the image cross section with a background subtraction. So in these two cases, you can understand the differences. So first, the advantage of background subtraction here. So quickly, I'll show you one quick example, and then I'll ask you for the questions, I guess. So this is a blood sample. If you look in the 3 dimension, it's like this. And once you do a background subtraction of it, let's put an arbitrary value. I'm just showing it for you to understand the feel, get a feel of these things. So you're able to identify the valleys and peaks in the blood cells. Similarly, in the case of a gold wire, this is without background subtraction. If I take a 3D of it, you don't see much information into it, much clearer information into it. But if you do a background subtraction of it, you extract and try to see it. Sorry. So you can understand how it looks like really. Okay. So these are some of the things which you should do while you're carrying out any kind of Raman measurement or the AFM measurements. Okay. I think I'll stop here. I understand that there is a lot of people from different background. So kindly, I would be more happy to ask again, answer your questions. And to understand, I'll just quickly share one more information for you. Please feel free to go to the website raman.oxonist.com, and there is a lot of things you can understand. What is Raman technique? You can get information about what is happening in the case of Raman technique. There is a learning academy is there. There is webinars are available. There is Raman knowledge base is available. Or so in order to, for the what is the lot of information is available. And for PhD students who are attending this webinar, you can just try to click on application notes. Thereby you can understand what people are doing in this recently. For example, in 2D materials or in battery research. Some of you might be working on batteries, some of you might be working on MOS2s, some of you might be working in polymers. So I'll just quickly show you on work in battery. So see Raman image overlaid into a SEM image and things like that. So I request you all to explore the maximum of possibilities of Raman spectroscopy in your PhD research or in your studies and things like that, so that you can understand. See, all of us are talking about electric cars. In order to understand, have good electric cars, you can see, you need to understand what is happening inside a battery, a cathode, an anode, and separator. You need to understand what happens in a charged battery and discharged battery. So all those information you can get from Raman spectroscopy. So thereby, I strongly urge you to explore Raman spectroscopy more. And those people who have not yet ventured into Raman spectroscopy, I'll request you do a study on Raman spectroscopy. Try to understand what is Raman spectroscopy, because it has enormous potential. Okay, and then if in case if you have some doubts or something like that, you can talk to Dr. Sano. He knows my contact and he'll be able to channel the questions to me. Okay, yeah. Now I'm happy to answer your questions if you have any questions, please.
The section is open for clarifying your doubts. Please ask to Dr. Jemy, so you can clarify your doubts and.
I know that this was a quick presentation because in order to, because there is a lot of people from different backgrounds, so I could only give an overall presentation. But the data analysis part is really related to the Raman spectroscopy, and then the other one I just thought of showing you about the atomic force microscopy also.
Hello, sir. It was a very good presentation. I could get a lot of insight from your talk. I'm working in heterogeneous catalyst, basically in materials. So, can you hear me, sir? Hello?
I can hear you.
Yes,
sir.
yes, you are audible.
Like in this regard, I wanted to know by taking the roughness of the surface and also by taking the Raman imaging and from the bandwidth changes, can we correlate directly to the catalytic activity? Hello?
Yeah, thanks for your question, Sujit. The catalytic activity and all can be really understood from correlating Raman spectroscopy with the scanning electron microscopy images. Okay, SEM and Raman together. So what you can do is that you can make a sample, mark the positions on the sample, do a Raman. The same mark positions you can take it to an SEM. Then you can do it a correlation. You get an SEM data. You can correlate this data of these two. Thereby, it can give you multiple insights into what happens in the case of catalysis. Okay, I really urge you to look forward to those application notes, which I just showed you in the website. which will
Yeah, yeah.
really give you what can be done. It's an immense possibility.
Yes, sir. Like I've come across some few papers regarding AFM based on the roughness where they kind of correlate with metal-based catalysts,
That
metal
is
supporter.
AFM. You can use AFM also still on it.
Uh,
AFM from it also you can understand, because you will be able to understand what happens to the material when it's degrading, or when it is engulfed by the surrounding medium and things like that. You can get idea about the material properties also, or morphology of this material using AFM also. So
yeah.
if you're really interested, you can just jump into one of the machines in anywhere. Just see these possibilities. AFM Raman machines available.
Yes, yes, sir. Like right now, as such I have not come across maybe my literature service not that I don't have wide spectrum in that search, but I've come across AFM, but Raman and Raman imaging with AFM imaging combining together, those kind of particularly in heterogeneous catalyst comparison of catalytic activity, I have not come across. So that was my question.
There is a lot of possibilities available there. I think you can. Are you working in this particular area?
Yes, sir. I am working in this area, like heterogeneous material science and all.
Fine, fine, fine. Definitely, you are welcome to use the machine. You can approach Mahatma Gandhi University there in Kerala, or there is a machine in Banaras Hindu University. May I know you from where are you from coming from? Where are you studying?
I'm studying in Pune Prasad Institution and also affiliated to Christ University,
In Bangalore.
Bangalore, sir.
Oh, then feel free to come out to our demo lab in Bangalore. We'll show you a lot of possibilities.
Where, sir?
We can get our contacts from the organizers. It's in Bangalore, the demo lab. There's a similar machine which is available in Mahatma Gandhi University in Kerala. So they'll be able to tell you more into that.
Okay, sir. And the software which you are using, it is commercial software or like academic software? Like it's a free software?
It's a software associated with the machine, basically.
Okay.
So thereby you don't want to go to a third-party software like Origin or anything like that. You can just directly use it and then get the data, use this on the software, and then show it to the audience directly.
Okay, sir. Thank you so much. And also, like, since we are like external users, so we don't get access towards the software. Like in that time, could you suggest a software which we can do like third party?
For AFM, Gidwin software is a very practical software which I also had to use it during my PhD. So Gidwin software is a good software for AFM basically, which is freely
Can you
available.
spell it, sir?
I just forgot the name. Let me just GWYDIN, I guess. Let me GWYDDION.
There's some network problems, sir. Could if you put it in the text message?
I'll put in the chat boxes. I'll put in the chat box.
Yes, sir. Yes, sir. Thank you, sir. Okay. Thank you, sir. Thank you, sir. Thank you so much. Okay.
I can see a question from Ashwati saying that, is it possible to have negative intensity for Raman? So to understand more into it, intensity, how does this intensity comes? Intensity comes when a material interacts with, you can have negative wave numbers basically. When a material interacts, when a light interacts with the material, the emitted light can be of higher wavelength or lower wavelength, or lower energy or higher energy. So you can have it either in the positive side or in the negative side. But intensity, generally, you can't have it, because generally you don't get a negative intensity. But after data analysis only, you will be, by mistake, you will be putting negative intensity with the data analysis. Generally, you don't get a negative intensity for the Raman spectrum. All of them is positive. So deconvolution, many of the cases, when you don't have a real, the spectrometer has its limit for getting information, or the resolution limit, or when multiple peaks are present together, or one peak is engulfing all the other peaks. In that kind of situation, you will have to use a deconvolution. Thereby, you will be. Let me just show you a small. I hope you can see my screen. So suppose you have a spectrum which is having a broad peak like this, and then there might be multiple peaks inside this which may not be able to be visible due to the main peak and things like that. So in order to extract information about the individual peaks and things like that, you can use deconvolution. To get more information about the individual peaks, that's the main use of deconvolution. Because each of these are chemical bonds, right? So these even minor changes in a bond. See, I was talking about that polydimethoxy PDMS sample, which is what happened to that particular SiO-Si bond and SiC-Si bond. The people wanted to understand what happens to these kind of bonds before aging and after aging. So each individual specific information you can get from the Raman spectra. And when multiple spectra, multiple peaks are together, you need to understand, you need to extract it outside. So in that scenario, you'll have to use a concept called as deconvolution. Yeah. I urge all of you to look into the recent articles in Raman Spectroscopy. You can go to our website, raman.oxonus.com, understand the recent application notes. See how people are using Raman spectroscopy for their research and their applications and things like that. Then we'll be able to get more output onto our research also.
Hi, sir. Hello. Can you hear me?
Yeah, I can hear you. I can hear you.
Yes, sir. Thank you for a very informative presentation, firstly. Sir, I'm actually stuck with the interpretation of Raman spectra. Same. I have prepared the sample and I've taken the I have done the analysis and I've also plotted. But then, is it like should we compare the Raman data, whatever we have got for our material, to the standard data like graphene or
What you have to do is that before doing any kind of measurement, make sure that your machine is calibrated. For that,
okay.
Firstly, you have to use in my case, I use silicon standard, which is easily available. I can get a peak of 520. Then I find out that I get the 520 peak, which will help me saying that my machine is fine. Even if you take it to any kind of measurement systems, take a spectrum of a standard sample, either be it graphene or graphene. You don't get it easily available, right? Silicon standard you will get easily available, a small piece of silicon. Get a standard, try to see where you're getting correct spectrum, 520.5. If you're getting that, then whatever you're not getting is because of the sample. So in some cases, what can happen is that there can be background. Your sample might have humidity, so your sample can have fluorescence. All those things matters. So
Okay. Because in the data that I've got, the peaks are only ranging from 1,000 to 4,000. At the peaks, I'm seeing it from 1,000 to 4,000. And quite of them are like sharp, like you showed in the presentation. And there is noise also in the spectra. So it was difficult to interpret the data.
Maybe the machine might not have been aligned properly. Maybe. Um, um, unless until I see the data, I am sorry I can't comment on it. But you can get in touch with the organizers. They can share the email address, and then you can let me know about the data. Then after seeing the
Okay.
data, I can tell you about the data.
Okay. Okay, sir. Yeah.
It's not
Thank
nice
you.
to judge on something which I have not seen. No, that's why.
Yeah. Okay. Yeah. Thank you.
So whichever machine you are going, use a standard sample. Either it be a silicon standard sample, or it be a CNT if it is available, or it can be any kind of polymer or anything. Silicon is the easiest available thing. Put on the machine, see whether you're getting the 520 peak. If you're getting the 520 peak, go ahead. Whatever you're getting, it's because of the sample. Okay.
Okay, sir. Yeah. Thank you.
Thank you. I'm just pasting that notes on battery research, and then I'll paste one thing on the 2D materials also, just for you to see. Raman spectroscopy is really a wonderful technique. It uh, it it ranges its applications from your daily activities like medicine to your tires to your diamond, and it has a lot of applications. So you should learn it for your research, and you should learn it for your career also, because it's made in India, right? CV Raman was made it. It's a technique from India, so be proud of it, and then explore the possibilities of it.
I think now we can end up the session. If anybody have to clear their doubts, please share it in the chat box. I
And to
would like
understand,
to.
yeah, just a minute. To understand Raman spectroscopy in a day is very difficult. It'll take multiple days to understand Raman spectroscopy and things. Once you understand it, you will understand the beauty of Raman spectroscopy. Yeah, thank you.
Thank you, sir. I would like to express my sincere gratitude towards Dr. Jemy James, who have taken time out of his busy schedule to grace this occasion and share his ideas on Raman spectroscopy. I need to mention my deepest sense of appreciation. Thank you, sir. I would also like to extend my gratitude to our principal, Dr. Manju Kurian, and our HOD, Dr. Smita Tangachan, for their unwavering support. I'm immensely thankful to Dr. Sanu Matthew Simon, Assistant Professor, Department of Physics, MA College, for your elegance of explanation. Finally, I thank everyone for taking this time to be here today and listening. Thank you all. The feedback form is shared at the chat box. Everyone feel free to fill up the form. Thank you. Thank you so
I
much,
also
sir.
would like to thank Mrs. Dr. Sanu and for inviting me, and Anju Ganesh for coordinating these activities with respect to me. Thank you very much. Have a good time. Feel free to let us know if you have some doubts related to Raman spectroscopy.
Thank you, sir.